So just to remind you of what we're trying to do, we're trying to understand why measuring the field at position X does not disturb the field at position Y if X minus Y is a space-like vector. So if X and Y are space-like separated. So we, okay, so let's say to see if measurements of phi of X disturb those of phi of Y, so we've discussed this, you need to compute the commutator phi of X, phi of Y, okay? And we've already calculated this commutator. We found that this is 0 if X and Y are space-like separated, and that means if X minus Y squared is less than 0, okay? But you might be a bit puzzled. You might say, why does this vanish? Okay, and the reason why you should ask, why does this vanish? And the reason why that's a bit puzzling is because we've just checked that particles can move faster than light. Okay, and that's because we have computed the amplitude for a particle created at X to be detected at Y, and we found that this amplitude is not 0 when X and Y are space-like separated. So why on earth, if I do something, so let's just draw a space-time diagram here. There is T, there is X. Here is the event X mu. Let's mark on this the light cone of X mu. So there's the light cone. And now let's put on Y mu. And what we're saying is, if we make a measurement of the field at X mu, we will not disturb the value of the field at Y mu. But why? Because particles can move between X and Y. So that's what we're trying to understand now, okay? So towards this end, towards understanding this result, let's study the commutator. So let's study the commutator, so phi of X and phi of Y. Now, you have computed this in one of the exercises, and what you learned is the commutator of phi of X and phi of Y is equal to a number. So I'll just call it C, and what I mean by this is it's a number, okay? So let's try to be completely explicit about what I'm saying here. So take a look at the mode expansion here at the top of the page. That integration measure, that's a number. The exponential, e to the minus ik dot x, that's a number. E to the ik dot x, that's also a number. The thing that is not a number is alpha and alpha dagger. So when I tell you that this commutator is a number, it may involve some integrals. It may involve stuff like d3k over 2 pi cubed 2 omega k. It can have exponentials, but it doesn't have alphas and it doesn't have alpha daggers. Now I want to remind you of something. If I take the vacuum, bra vacuum, I have a number, and I have ket vacuum, well, because it's a number, I can just take it out. And then I just get the brackets, the bra and the ket of the vacuum, and this just gives me the number because the vacuum is normalized, okay? So whenever I've got a number, I can always just sandwich that number between bra ket, between bra vacuum and ket vacuum. So this commutator, phi of X, comma, phi of Y, this is equal to bra vacuum, the commutator, phi of Y, and then ket vacuum, okay? And that's true whether x and y are space-like separated, time-like separated, or null separated. This is just a fact. And then this is equal to, well, let's just write out the commutator. So there's the first term in the commutator, and then we have minus the second term. So there it is. And if you remember, we just calculated this. This is what we call delta of x minus y minus delta of y minus x. Now, in the exercises, you have also studied this quantity. And if you remember, you argued that this vanishes if x and y are space-like separated. And that's because we can write this as delta of x minus y minus delta of minus x minus y. Okay, so that was the first observation. The next thing that we used is that delta of x minus y is Lorentz invariant. We proved that. And then finally, you guys proved that if x minus y is space-like, so x minus y squared is less than 0, then there is a Lorentz transformation, let me call it lambda, such that lambda acting on x minus y mu gives you minus x minus y mu. And you even spoke about how to construct that Lorentz transformation. So this term over here, this is actually equal to 0. But something to note, something that's very important, is that each term is non-zero, but exactly the same size. And that means they cancel, okay? So we're not getting 0 because each term separately is 0. No, each term is non-zero. And that tells us that particles can move faster than light, but there's a cancellation between two terms. So let's try to understand what this cancellation is. We want to interpret these two terms, and the best way to do that is this term over here, number 1, which is this term over here, that cancelled against number 2, which is this term over here. So let's think about what these terms 1 and 2 are. So I'm going to draw a space-time diagram. There we are. This is time, or x0. This is space, or x1. I've got x sitting here, and I have got y sitting here. So two events in space-time. Now, for the first term, well, let's start with the second term. We create a particle at x, and we destroy it at y. So what does this correspond to? We have a particle which is created at time tx, and it is destroyed at time ty. Now, what about this second term, term number 1? Okay. Well, term number 1 corresponds to a particle which is created at y, so it's created at ty, and it's destroyed at x. It's destroyed at tx. So it is destroyed before it is created. Well, we just discussed that, and that means we have an antiparticle moving from x to y, okay? And what happens is this particle and the antiparticle amplitudes exactly cancel. So when x, let's say, and y, when x and y are space-like separated, then the commutator vanishes because there's a particle and antiparticle contributions. They are identical in size, but we take the difference between them. So these two contributions cancel. So in order to have relativistic causality in our theory, we do have relativistic causality. If we do something at x, we can't disturb what's happening at y. But that's not because particles cannot move from x to y. They really can. They can move faster than light. But every time you have a particle moving, you also have an antiparticle moving. And these two effects cancel to give us relativistic causality. So this is how we get relativistic causality. And if you want relativistic causality, your theory must include antiparticles. So antimatter is a very basic prediction of any quantum field theory. And to have this cancellation being perfect, the particle and the antiparticle must have exactly the same mass. They must have exactly the same spin. There are some quantum numbers like charge where they can differ. And you know from our discussion of electrons and positrons that if the particle has charge Q, then the antiparticle will have charge minus Q. So the charges can be opposite. Now, the fact that the masses must be the same, the spins must be the same, but the charges can be opposite, that is embodied in a very basic theorem in quantum field theory. It's a theorem. It's called the CPT theorem. And any theory that is Lorentz invariant, any quantum field theory that's Lorentz invariant, must obey the CPT theorem if it's going to be a sensible theory. So, and in particular, if it's going to have relativistic causality. And this theorem forces particles and antiparticles to have the same properties, same mass, same spin. If one is charged, the other must be charged, although the charges can differ by a sign. So now we understand how the theory manages to respect relativistic causality, even though particles can move faster than light.